at the end of the plate, right? The calculation is only approximate. It become true when this thing is infinitely long, and this is infinitely big, right? What you have is a fringe effect, and it's the electric field here interacting with the induced polarized charge that is in there. Yeah. But we don't have to analyze it kinematically that way. We can just use conservation of energy, right? So for the first part of the problem, all you need to do is find the difference in the potential in the potential energy.
Yeah, that's right.
That's about it. Everybody know how to solve or?
Yeah.
So there is a decrease in the potential energy, right? Because the potential energy for at the beginning, the potential energy is just given by 1/2 epsilon naught E squared, right? Times the volume, right? Then the volume is just A times S, right? Okay, because this has an area A, and then thickness S. This is problem 371, right? This is 71?
Yeah.
Okay. And at the end of the day, this is at the beginning, initial, final, what happened is that this whole thing is inside, right? Okay, and the conductor has no inside the conductor there's no field, so you have a reduction in the energy. You have instead of half E squared A S over 2, is that right?
Yeah,
Something like this, and the difference will give you the difference get converted to kinetic energy, right? So this thing is slanting in that direction, okay? This is a good problem, right? This thing actually will oscillate, right? Because you have a kinetic energy when it's completely in. That's a midterm problem right there, right? You know?
No.
That's how you come up with the midterm problem. Just think about the problem, just try to understand it. So you see, I'm giving this a midterm problem, right? At some point you have kinetic energy, this thing will overshoot, right? And then it will get pulled back in, right? And it will oscillate.
What will oscillate?
This conductor, this lamp, right? It starts with the high potential energy, right? And then it converts all the potential energy of the electric field into kinetic energy, and it will overshoot, right? And then it gives back its kinetic potential energy, and then come back down, and it will just oscillate.
What?
But this is not part of the problem.
What makes it come back down?
It's asking you for the field.
The field again, the fringe field on that side.
Oh, I see.
Right, but you don't have to analyze it that way. You don't have to analyze it dynamically. You can just talk about energy, conservation of energy. Right?
What's the kinetic energy of the? I guess it makes sense to me, like intuitively, like when you put the conductor inside, like the side that's touching the negative charge will like polarize to the same opposite. But like, is there a way to show that, like with Gauss's law and stuff? Like, because you have to like assume that putting the conductor in won't make the field outside non-zero, right?
No, it won't. No, it won't. Right? I mean, this is very difficult to analyze. Right? I mean, yeah, once the whole thing is in, it's easier to analyze, right? Because when it's still outside, you'll polarize a little bit, right? So there will be minus sigma here. It will not be uniform, plus sigma over there.
Well, no, but like once it is in, like.
Oh yeah, then you can use Gauss's law, right? I mean, if you have a configuration like this, right? Perfect conductor is always true. E inside is 0, right? So you do your Gauss's law, and then you will find that this is minus sigma, this will be plus sigma, and this is minus sigma, right?
Well, I guess my question is, if you did Gauss's law, why is it that you can assume that putting the conductor in won't change the fact that E zero like on the other side of the plates?
Oh. No, the E is only 0 in here, right?
Oh, okay.
So, and E is always 0 on the outside. Originally, E is 0 here.
Yeah.
And E is 0 there, right?
Yeah.
You have these two charges, right? You bring this in, right? It will just basically polarize the conductor, and then you have plus sigma minus sigma. So that neutralizes this part. So you have minus sigma on that side.
Right.
So basically, what you have is that this conductor completely short this other plate. So you just left with this two plate,
Oh,
right? Meaning that this conductor basically bring this plate here over here, right? You start with this two plate, right? This is a conductor, say this is a very thin conductor, this is another conductor, right? You bring this thing in, right? Basically, effectively what you have is you bring this left plate halfway in the middle.
Are they the same size?
Sorry?
Is the slab in the middle the same size as the other slabs?
Yeah. I mean, you pretend that the whole thing is extends to infinity. Right? This analysis breaks down a bit when you farther out. But it's actually important because that is the mechanism for this thing to slide in.
Mm-hmm.
Without that, it will not slide in. Without the fringe effect, it will not slide in.
so what's the difference between having like this situation where you have a conductor in between the plates and just making one of the plates like really thick?
No difference.
There's no difference.
Right, yes. I mean, in a real situation, right, this is the part that we didn't finish discussing in the lecture when we talked about the capacitance matrix, right? I mean, in reality, this thing is pretty thick, right? There is no such thing as infinitely thin conductor, right? So this is also a conductor, right? So, but all the charge will concentrate on the right-hand side of the conductor. I mean, you can analyze this, go through the derivation of, go through the example on capacitance matrix on Purcell. It'll become more clear. But yeah, sliding this in basically, as far as the problem is concerned, remove this left-hand part of the problem, right? You just left with minus sigma over here, and you can think of the plus sigma over here, canceling the minus sigma on the other side. But back to the problem at hand, for part B. For part B, things are different. It's actually tricky, right? What happened is what you maintain is not the charge difference, right? This is how what you maintain on part A. On part B, you maintain potential difference. So you have this, as I discussed in lecture, you have this demon, right? This maintain the voltage. Okay? And so B, 0, and you have an electric field, okay? So what happened here, as the slab goes in, what happened? Okay, so what happened is, so let's pretend there's an electric field here, so the slab has to go in from that side, right? So as it completely goes in here, then you only have electric field on this side, right? And it's 0 in here, right?
Potential difference still has to be the same from the edge to the slab.
The potential difference still has to be the same, right? Therefore, and potential difference for an infinite slab, the potential difference here has to be equal to E times S originally, right? At the beginning, this is initially. Right? EI is here, right? And when this whole thing is already in, you still have the same potential difference, but you have another electric field because now S is S over 2. Right? Because you only have you only integrate from the right edge to this edge of the conductor. Right? Okay, so EF has to be double EI in this case. Okay. So what happened to the potential energy? The potential energy goes as what? 1 over epsilon naught E squared times A times S, right? Okay. So this is initially, but in the final case, you have 1/2 epsilon naught E final square A S over 2. Right? So the final energy is actually twice the initial energy. So what's happening here? Right? what happened here is the guy here has to do a lot of work. Right? And then you can calculate that, right? So how much work does the guy do? Right? So wait, we did the kinetic energy, right? The initial energy. Well, no, that's another problem, right? So how much work does the guy do? At oh, battery. Right? You can just start doing this little battery from now on. Instead of this. I like it better too because we don't understand it yet, right? Let's keep it that way maybe. So how much work is it? Electric field double. EF becomes 2EI, right? Then what happened here? What happened is that the guy here has to supply more charge, right? You have to put double the, so originally you have minus sigma I here, right? And then suddenly the E field double, so this becomes sigma final, but recall that E is equal to sigma over epsilon naught. Right? Therefore, it's this double. If you have twice the electric field, then you have twice the sigma. Right? So sigma F is equal to 2 sigma R. Right? So how much energy do you supply? How much work do you do here? The work done by the demand then is just the total charge, right? The total charge transfer. He has to transfer. He has to transfer 1 sigma, well, I guess sigma times the area, okay, from the left side through the battery here, right, and put it on the other side, right? So the work done is twice the charge to, not twice, right? It's for the sigma, the difference here, right? The difference, the delta sigma is just sigma, right? The original sigma, right? So it's just sigma I area, this is the charge, right? This is the charge that we move times the potential. Right? And this becomes sigma I is just EI over F times epsilon naught A, and V is the original EI divided by times S, right? V is just the original EI times S. So you'll see there is a work done here, and what happened is work done by Diemann. So work done plus the original potential energy, electrical potential energy, right? Before the slab goes in, has to be equal to final plus kinetic. Right? This is just conservation of energy, right? And for now you take it as true, but you can show this, and certainly you show that this is true. Right? So you can calculate work done, you know the initial energy, you know the final energy. This final energy is actually, this U final is greater than UI, right? But you supply some work, and then you still get kinetic energy out.
So the voltage is still staying the same, but since we're supplying
Yes.
twice as more
Yeah.
to the electric field, it's going to run off faster, right?
Right, so the guy has to work very hard, or somewhat hard, to maintain this potential difference, right? As this thing goes in, right, to maintain that potential difference, he has to transfer charge from the left to the right, right? So for this to happen, right, not only the guy has to supply energy to give kinetic energy to the slab, but he has to do it in such a way that also increase the potential energy of the system. So it's a double more work.
Wait, you have to increase the potential?
Yes,
I thought you have to maintain it constant.
you maintain the potential constant, but the potential energy increases.
Oh, right,
That's what
right.
we-
Yes,
Yeah,
that's what we just did. That's what we did here. Sure, because the electric field double, right? And then potential energy stored in the system is goes as E squared times the volume. The volume shrink by half, but the electric field doubles, so E squared for 2 volts.
And the difference between this case and the first case?
The first case is more straightforward because there is no
worry.
demon, right? There is no demon. It is only plus minus Q.
So there's no worry about this one.
Yes, yes. I think that's the most difficult part of chapter 3, right? Any other question on this? How about 68? Is 68 difficult? 68 is a constraint problem. Can I erase some of these? We're going to which one can I erase? Is that you have a cylinder of radius A and B, right? And question asks for what's the best configuration to maximize the energy stored in the capacitance. In this capacitor here of line L. Does anybody remember the formula for the capacitance of a cylinder?
Oh, we have it in here. 2 pi epsilon L.
Epsilon L.
2 pi epsilon L.
So the 2 pi you can never remember, but you should remember it's epsilon not L.
Over the natural log of
Over A? Oh, which one is A? Which one is B? Which
The
one
longer one
is
is
A.
What?
No, they said outer one's A and inner is B.
Oh, the other one is A.
But it's 1 over Ln.
Okay, so this is.
No, like the Ln's in the denominator.
Sorry?
They put Ln in the.
Yeah.
Oh, yes, sorry, what am I thinking? Okay, you can derive this, right? It's not that difficult. But we want to do a shortcut. It's only 1 hour here. So what happened is that this problem is a constraint. You want to maintain the situation in such a way that the electric field at RA or at RB has to be less than E naught, right? This is a reasonable constraint for any practical problem, right? You want to keep the electric field limited because otherwise you might have a breakdown, right? And you want to position P in such a way that you maximize potential energy. Okay. So what happened here? If P is equal to A, there is no potential energy, right? If P is equal to A, U is equal to 0, right? Because basically you don't have a capacitor, right? And if P is equal to 0, right, then also U is equal to 0. Because when P is equal to 0, remember electric field goes as 1 over R, right? In this case, electric field goes as 1 over R. So if I shrink P all the way to 0, this lambda over R, I better make lambda goes to 0, right? Otherwise, the electric field goes up, right? This has to be less than E naught, right? So in order for that to happen, lambda has to be equal to 0. There is no electric field. U is 0, right? So the problem is like this. This is A. So this is
Yeah,
This is A. This is B, right? This is the range of P. This is 0. The problem goes like that, and you just have to find the maximum. Right. Okay. And how do you do that?
What just happened?
Sorry?
What's the A and what's the B?
A is, I got confused myself too. A is this is that radius, right? P is this radius.
So I mean on the graph.
Yeah, since the graph was as I vary p, right? When p is equal to 0, instead of calling it p, maybe you call it, well, it's called p. But p can vary, right?
Oh,
You
okay.
vary p from 0 all the way to a, right? So when p is equal to 0, the energy has to be equal to 0 because otherwise you have a breakdown, right? Because E has to be, the constraint of the problem is that E has to be less than something, right? And then when B is equal to A, you don't have a capacitor anymore, right? And then at some point, hopefully the problem looks like that. I'm just guessing.
What if B is very, very big? It's like
Oh,
almost not having a capacitor also.
oh no, if B is very big, then you have to flip the situation.
I see, sorry, I think.
A is the maximum
Yeah.
here, right? Okay. So, there are many ways to do this problem, not many, at least two. You can find the energy, just the same way, right? 1/2 epsilon naught E squared T volume, right? Okay, I'm starting to write in volume as an application suggestion. Or since this is of course if you need an exercise to do from chapter 2, since we're on chapter 3. Are we on chapter 3 now? This is chapter 3, right?
Yeah.
If this is chapter 3, then U is what?
CD squared?
CP squared. But in this case, it's more natural. It's more natural to have to do it Q squared over C, right? Because what you're doing is you're maintaining you put a plus Q here, minus Q here. Okay. But either way, it doesn't. At the end of the day, it doesn't really matter, right? It's easier this way. So you'll find an expression that depends on V. You just have to differentiate with respect to V. Right?
To get more.
To get the X element here.
Oh, yeah.
Yeah. So this is the point where du V is equal to 0,
Oh, that's pretty good.
right? This is an accident, and this will be the maximum. Hopefully it's a maximum. You just have to show from the curve, right? Hopefully it's not like 10. I think it's like this, but that I don't know. I haven't done the problem. Okay, and set this equal to 0, and you find the P is. And where this is going to be? Probably halfway, right? This is probably going to be over 2 or something like that. I'm just guessing. Right? It cannot be way too. It cannot be 2 close to 0. It cannot be too close to that. Right? So it's probably like a over 2, over 3. I don't know. Okay. So that's the end of chapter 3. Sorry?
Okay, you plug in C into the.
Yeah, you plug C in here, right? So instead of doing it this way, you can do it this way too. If you need an exercise, if you want an exercise in calculating energy based on electric field, just plug this in here,
Yeah.
right? And no, you have to also find the electric field. So at some point, there is a constraint, right? This problem, of course, will not work if you just do it that way, right? There is electric field. You have to find the electric field at RA, and it's equal to what? Lambda over 2 pi epsilon naught RA, right? Is that right? Is this the right formula? And lambda, in this case, is going to be Q over 2 pi RA L, right? Something like that. You have to constrain the problem, right? Meaning that E, you have to find the expression for E.
So does that just determine the Q that you end up with?
Yes, that, correct. That's put inside. This expression here determine the Q in here. right? Because that limits the Q. For a particular B, oh, sorry. This is RB or whatever, B. Right.
Oh, that's also really important.
Okay.
Yeah.
So this limit the Q, right? And you can just substitute this expression here. You just because what you want is a maximum energy, right? So you want to keep the whole setup in such a way that the electric field here is close to the limit, right? That's how you maximize energy anyway, right? As long as it's not greater than E naught. Okay. So I guess we have another discussion on tomorrow. Any other question? I think chapter 4 is a bit more difficult. No? I don't want to scare people.
No, chapter 4 is about
It's tricky, right? And do you guys want to change the subject to chapter 4 and then go back to 370 tomorrow maybe or something?
Yeah.
Okay. Did you guys think about the quiz problem that I did at the end of lecture yesterday?
Should be the first. Should be the first.
Yeah. But let's not get distracted. I used to like puzzle a lot. I think like puzzle so much nice. I get really good. Like business problem here. Maybe it's better to say. So you have this is one of the problems, right? So you have resistor everywhere forming a cube. Okay, at the edge of this cube you have resistor, all the same resistance R. Right? Okay. I don't know how useful this is. The other problem, the next problem is actually useful. This is more like a matter, this is more an exercise of your understanding of things. Right? So say for part A, you're supposed to find, so you connect this to a battery, that is for ease of discussion. Right? To the opposite vertex. Okay? Yeah, to the opposite. And you have to find the equivalent resistors. What is the equivalent R here? Okay. And then the other, this is part A, and part B is when you connect this over here, right? This is part B.
Oh, so you get rid of the first connection.
Yeah, you get rid of that. So there are three problems, right? What is the equivalent resistor across these 2 points? What is the equivalent resistor across these 2 points? What is the equivalent resistor across these 2 points? Right? So as this is A, this is B minus C. This is B for the second part, and then this is B for the first part. Right? Any idea how to solve this problem?
C.
I think A is the issue.
It seems like the easiest.
That's the most symmetrical. Well, I don't know. I mean, they're all, in the end, once you get a hint, this becomes a very easy problem. Right? Does anybody have any idea how to solve this problem? Have you seen that before in your high school physics? Or, no?
Is the problem reduce that to one equal to?
Yeah, reduce this to, in the end, reduce this to a problem like this.
And
What is the equivalent resistance here?
Wait, what are all the P's?
Oh, sorry. This is so there are 3 parts of this problem.
Oh,
There are 3 parts.
define what equal.
So part A is what is the equivalent resistor between this diametrically opposite vertex. Across the cube, and part B is finding it between this and that. Opposite vertex along one of the face. And part C is what is the equivalent resistor between these 2 points. Right? I read this problem. Yeah, adjacent coordinates, right? This is part C. So this is part A, part B, part C. Completely different problem. You think about it separately. So once you know how to solve one, you pretty much know how to solve the other too. How do you do it? No. Do you guys want to know a little bit about this, or do you want to think about it yourself?
Yeah, you can open up the cube and like have it out.
It's not the shortest path. It's not that. Okay, let's erase all that. Let's erase this. I mean, if you want to analyze things, do this and that, right?
Yeah, so first we
You have current going that way, that way, and that way, right? And then at some point the current also combine again, you know, so over here, you know, this current is a sum of this current and that current, and then this current is a sum of this current and that current. It's confusing.
Yeah, I think.
Which term?
Sorry?
Yeah.
I mean, you can do all the Kirchhoff law, right? Remember the Kirchhoff,
Yeah.
the two Kirchhoff law? Is it called Kirchhoff or definitely? I don't even know.
What happened to
Yeah,
the
called
Kirchhoff, the two Kirchhoff law. Right? So the current, the sum of the current has to be equal to 0, right?
One like,
On a branch.
and then in EC40, they teach us how to do like nodal analysis. And they'll give you like a minimal set of equations to solve that kind of stuff.
Yes.
It'll probably be easier than just randomly guessing at which current laws to use.
Right. Yeah, you can do it that way. Basically, you have n unknown. You have to find n equation, and the matrix will be non-singular, and you can always solve for it. But
Yeah.
I don't know. I don't want to solve it.
Well, I think it's like, if you can just like write it down and then like type it into a computer and solve it, that might be the easiest thing to do.
Okay. Yeah. But that's not the point. The point is actually. So wait. Let me just for everybody else, just to remind you of the Kirchhoff law, right? So if I have a branch, if I define current to be all inward, right? I1, I2, In, right? Then the sum of Ij, say Ij from 1 to n has to be equal to 0, right? So current in has to be current out, right? And then also across in a loop, the sum of the voltage drop has to be equal to 0 also. Right? And that you can solve any certain problem. It's boring. It's not really that. But I don't know. I mean, E40 interesting. E40
Yeah,
is very
that's
interesting.
just all you do is solve that stuff.
Okay. But let me give you do you guys want to think about it for one night and talk about it again tomorrow, or do you want to think now? Right? Think about it, right? This is interesting. It's an interesting puzzle.
Okay, wait, so you're saying there's like, so you're saying there's an easy way to do that without using.
Yeah, there's an easy way. You have to think about it physically, right? Think about it physically, what happened, and there's an easy way. There's a shortcut. You don't have to solve any of this, you know, and which you can do, but, you know, I don't want you guys to explore that path, unless you feel like it. And the other problem is along similar thing. You have an infinite ladder of resistors. So let's talk about that tomorrow also then, and then what else? That's it, no? The two light bulb thing is very easy, right? It's a bit counterintuitive, but you can solve for it. This is the problem I gave you yesterday. If this is a light bulb, same light bulb. So instead of drawing the resistor, I'm drawing a light bulb, right? And the question is, which one is going to be the brightest? A, B, C. Which one? They're the same light bulb, you get the same R, same resistance. Which one is the brightest? It's not that difficult. But number 38 is somewhere along that vein. The hardest part about this problem is which one do you guys think is the hardest? Have you guys looked at this in chapter 4 yet? It's the silicon junction diode. It's actually not that difficult, but it does mean it's a real problem. Right.
Wait.
Yes, as you see that, as you get older, it's already not puzzle, become less interesting, real problem become more interesting. Yes. But I don't know which one is interesting. Silicon diode junction. You don't have to know much about PN junction. You just have to know, for this problem, you just have to know a few things. So yeah, this is P-dope. Do you want to specify which one is which? It doesn't matter. You have P-dope silicon, and you have an N-dope silicon here. Okay, so this P and this form a diode, right? So anybody knows about this or a little bit? Who's an electrical engineering major? Many is an electrical engineering major.
No, I'm not. Okay. Oh, yeah, he talked about it.
So this is diode, so current can only flow this way. Remember we talked about vacuum diode?
Yeah.
Vacuum diode. This is actually diode made from semiconductor, but you don't have to know any of this, right? All you need to know is what happened. What happened here when you connect these two at some potential difference, right? So there's again the demon here, right? So what happened is there will be a layer here. There will be a positive. It's called hole. When you positively dope silicon, the carrier is actually a hole. You'll learn this eventually if you take a solid state physics class. It's an absence of electron, right? But think of it as a positive charge for now, right? And then on the p-dope side, you have an electron, right? So that's all you need to solve this problem, and then you can throw away all the dressing of the interesting practical stuff or interesting real physics stuff, right? So plus rho, and then here is minus rho, right? It's basically think of it as two slabs, positive slab, negative slab, and you're supposed to solve for the potential everywhere. Right? I don't even know why this is problem for chapter 4, now that I think about it. Right? So do you guys have an idea how to solve this problem? Right. And then they give you all the parameters, right? They give you all these distances. So let's consider this x, right? So this thickness is going to be whatever that thickness they give you. Is it s? Whatever, right? It's in there somewhere. Yeah, so it's s, and then this is also s, right? Complicated, maybe, but you've solved this one of this problem before, right? In fact, there's two variants. The first one is when you have, at the extreme, when this becomes an infinitely thin slab, separated by distance s, right? Let's call this s over 2, right? And sigma, you know how to solve all this problem, right? What is the potential here? It's minus s over 2, the potential goes like this, right?
Yeah.
0 here, and then constant here, and there is a slope, linear here, and then it goes as sigma over epsilon naught is the slope, right? The slope is the electric field, right? So basically this is a swing, and also just we did this problem also, right? I have sigma here, just one sigma, not just plus sigma, right? Then the electric field, we found the electric field. If this unfrozen the electric field goes, how does the electric field goes like this? Right? It's sigma over epsilon naught here, 2 epsilon naught, minus sigma over 2 epsilon naught, and it's linear here, right? Okay? And what's the potential? If you remember, I think I did this in lecture, the potential. Did we do this in lecture? I think we did this in lecture. Maybe. I forgot. Then the potential goes like this. It's quadratic here. Right? And it becomes linear here. So the linear part, when you take the derivative, it becomes constant electric field. And the quadratic part of the potential gives you the electric field as linear inside. Right? So if you look at these two solutions, you sort of can guess that for this problem here, this silicon problem, plus minus, right? Then the potential will look something, I don't remember, I think they, just for simplicity, let's call it, so they agree with this problem, right? This is minus, that's plus, let's make this minus and this plus, right? So this is 0. So instead of something like this, you probably have something like that, right? You know, smooth things out a little bit. And this is the shape that you want to solve for. Right? You solve for it separately. You solve it for region 1 and for region 2. And then you have to make sure that they meet in the center. The potential has to be quadratic, right? In general, they have to satisfy. Is it time yet? Yeah. Just 1 second. They have to satisfy the Laplace equation. Right? So P has to go as either constant plus x plus ax plus bx squared, right? This is a general solution to the Laplace equation, right? Because, sorry, B is going to be minus rho over epsilon naught, right? You only have dependence in x. So you have to solve for this in this region, in that region, and make sure that they're in the center. And that will be the solution. It's kind of tricky. I think this is one of the trickier problems. If you have any question, we'll talk about it again tomorrow at 4.